Swayam Prabha. Digital India. Educated India.
Welcome friends, welcome to the course Introduction to Sampling Theory. So you can recall that in the last couple of lectures we had considered the ratio method of estimation, and we had learned that how are we going to employ this method of estimation, and we also have seen that this ratio method of estimation is going to give you a better estimator in the sense of having a smaller variability in comparison to the sample mean. The sample mean that is obtained under the simple random sampling. Right. So that was our objective. Means if you remember, once we had talked about that our basic objective is to control the variability, and the variability can be controlled before drawing the sample observation, after drawing the sample observations. So after drawing the sample observation by simple random sampling, we have learned how to employ the ratio method of estimation. And if you remember, once we also had discussed that this ratio and regression, they are the methods of estimation, they are not the methods of sampling. So I have now illustrated that how one can employ the ratio method of estimation when the samples are drawn by simple random sampling. Now these are the estimation methods, so they can be employed in all sorts of sampling scheme. So up to now I have considered the ratio method of estimation when the samples are drawn by simple random sampling. Now in the lecture today, we are going to consider the ratio method of estimation when the samples are drawn by stratified random sampling. So now at this stage, means I would like to inform you that in order to understand this lecture, this is very important that you have a quick revision of the basics, fundamentals and results of the stratified sampling, because I am not going to give you the proof or derivation, but I will use the expressions directly over here. And one thing more, you know that in stratified sampling we are trying to draw the samples by simple random sampling, and we are going to employ the ratio method of estimation. So you also need to have a quick review of the results what we have proved in case of ratio method of estimations when the samples were drawn by simple random sampling, and I will be using those expressions here directly. Right. So if you have not revised them, I would request you first revise them and then continue with this lecture. So okay, I begin this lecture, and before beginning I can share the information that if you want to download the slides of this lecture, you can go to my home page, and the slides in the PDF format are available there, and you can download from there. And these slides are uploaded at this address, home.iitkac.ac.in/SHALAB/SP. And if you are facing any problem in coming to this site, then you can also scan this QR code using any free application on your phone, and then you will come to the same address. And if you are facing any problem, then I would request you that you please go to any search engine on the internet, type my name over there as Shalabh and IIT Kanpur, and I hope you will come to my web page. Now first you have to think that what are you going to do when you want to apply the ratio method of estimation in the stratified sampling setup. So obviously there is no issue. You have to understand that you have a population. This population has been divided into say smaller groups which are called as strata, and from each of these strata you are going to draw the sample. So, this is your here the basic setup, and you can recall that this is what we had done. So, we have here a population of size capital N and which is divided into say small k number of strata 1 to k, right. Now, the objective is the same. The objective is that we have a steady variable y on which we have some sample of observations, and based on that we would like to find out the population mean of y. That means, we want to estimate the population mean capital Y bar, but now we want to use it and we want to estimate it using the ratio method of estimation. So, now as soon as you say that you want to use here a ratio method of estimation, that means there are going to be two variables is x and y. So, this population means earlier which was containing only the population units y1, y2, yn, this will also contain the unit x1, x2, xn, right. So, this the same population which I was earlier denoting as like this, now I can partition it into two parts, one for y1, y2, yn and say another for x1, x2, xn. And when you are trying to divide it into different strata, then the similar thing will be followed here, that every strata will be divided into two parts, one for y's and one for x's. And from there, when you are trying to draw here a sample, the sample will also have observations on y1, y2, yn and x1, x2, xn and so on. And this process will be repeated for all the k strata. So, that is the difference now, that every strata will have two types of information, one on y's and say one on x's, and then you are going to draw the sample on y's and x's both. So, that is what is the setup. Now, where is the problem? Means what do you think that will be the difference when you are trying to use the simple random sampling or stratified sampling, right. So, now we fix our sampling methodology, that in such a case we are trying to draw a random sample of size small ni from the ith strata, and the size of the ith strata is capital Ni. For example, this strata first one will be of size n1, then n2 and so on. And we are trying to draw the sample by simple random sampling without replacement for y's as well as for x's, right. So, now what is the problem? So, in order to explain you the issue in the application of ratio method of estimation in stratified sampling, I have just drawn this picture over here. Means I have drawn it so that I can save the time here. So, you can see this is the same picture which I have just explained you, that I have here a population. Now, this population is divided into two subgroups, one for x and one for y, right, and there are capital a number of units in the population. And now this population has been divided into different strata. Suppose this is stratum 1, stratum 2, stratum k, and now this every stratum is now divided into x and y. There are two partitions, right, and the number of units in the stratum 1 is capital N1, for second stratum it is capital N2, and for the kth stratum the number of units are capital Nk. And if you ask me how this strata have been constructed, we have used the same philosophy of stratified sampling, that they have been constructed using the concept that they are within homogeneous and between or say among heterogeneous. So, there is no issue. Whatever we have studied in the case of stratified random sampling, that will be followed here. Now, what I do, that from each and every strata I try to draw a simple random sample. By now I can say that we are trying to follow simple random sampling without replacement. So, now you can imagine that this sample will also have two compartments. One compartment for keeping the value of x's and another compartment for keeping the values of y's. Right. So, in case if I am saying that we have drawn a sample of size small n1 number of units from a population of capital n1 number of units, that means we have observations here something like x1, y1 up to here xn, yn. But now this n will become n1. But you also have to associate one more subscript here to indicate the unit number and the strata number, but that we will do later on when we try to formally define all the symbols. At this moment I am trying to give you the basic idea, the basic fundamental. So, each and every this symbol will have the paired observations. Right. Now, in case if you want to apply the ratio method of estimation, you simply have to think that there is a population of size capital N1 and from there you are trying to draw here a sample of size small n1. And now you have to apply the ratio method of estimation. So, obviously from this sample I can compute the sample means of x's, sample means of y's, and we also need the population mean of x's. So, that will correspond to the population mean of auxiliary variable in the strata, in the, for example, in this case the first stratum. So, I need here three pieces of information: sample mean of x, sample mean of y, and stratum mean of this x. Based on that, now in this first case I can define the ratio estimator as here say y bar r hat, and I can call it as say here 1. So, y bar r hat 1. So, this will become here small y bar upon small x bar, they will be replaced by small y bar 1, small x bar 1. That means the sample mean of y and sample mean of x from the stratum number 1 and into capital X bar 1, because this is the mean of the population corresponding to auxiliary variable. So, now the population is here the first strata. So, this x1 bar will be the stratum mean. And similarly, I can do the same process in the second stratum and similarly in the kth stratum. So, practically now you can see here, you have here k possible ratio estimators. What are those estimators? 1 y bar r1 hat, y bar r2 hat, and y bar rk hat. And now you want to have a single estimator because you want to estimate here capital Y. So, now the problem is this, is how you can combine these y bar r1, r2, rk. So, one option is that I have considered y bar r1 hat, y bar r2 hat, y bar rk hat, and these are the estimator as if I have employed the ratio method of estimation in each and every strata. So, now I have got here k strata and I can combine them, just try to combine them. Now, the question is how are you going to combine them? So, in this case if you try to see, first I am trying to estimate the ratio estimators separately for each of the strata, and then I am combining them. So this type of estimator will be called as separate ratio estimator. Yeah, how to combine them, that we will try to discuss, but I am simply trying to give you an idea that what really are we going to do. And similarly, now if I try to take another option, the another option is that here that we have here the values of x1 bar, x2 bar, xk bar and y1 bar, y2 bar, yk bar. Now I can combine them using a stratified mean, right? Means I can define here x bar, say st, and for this y1 bar, y2 bar, yk bar, I can define here y bar st. And now I have got here this x bar st and y bar st. So I can define here a ratio estimator as y bar st upon x bar st, and then here I can take the population mean. So in this case, what are you trying to do? You are first trying to combine all the sample means, and then you are trying to construct the estimator. So this type of estimator we are going to call as combined ratio estimator. So we are going to consider here two types of estimator. One are based on the concept that first you try to employ the ratio method of estimation separately in every strata and then try to combine the estimator. And the second option is that first you try to combine all the sample means using the concept of a stratified mean, and then you try to define the ratio estimator, right. So we are going to discuss here two types of such construction, and these are the actually basic methodologies, and they can be employed in different types of setups also, right. So now we first fix our symbols and notations. So now we are going to indicate that a small yij, that is going to indicate the jth observations on steady variable y from the ith strata, and xij is going to indicate the jth observation on x from the ith strata. And yeah, means we have got here k strata, so I goes from 1 to k, and we are trying to draw a sample of size ni from the ith strata, so j goes from 1 to ni. And now we are interested in estimating the population mean capital Y bar, but now it has to be based on the philosophy of stratified sampling. So we are going to consider here two types of construct of estimators. One is separate ratio estimator, and say another is combined ratio estimator. So now we will discuss these estimators one by one and will try to derive their properties. So in the case of separate ratio estimator, as I discussed, we first employ the ratio method of estimation separately in each strata, and then we obtain the ratio estimator, say here y bar hat ri for I goes from 1 to k. So we will, so you will have here y bar 1 r1 hat, y bar r2 hat, and up to here y bar rk hat. And yeah, in these constructions we have to assume that the strata mean x bar I is known to us. Now once we have obtained the ratio estimators separately for all the strata, then we can combine them using the weighted arithmetic mean, and this will give us the separate ratio estimator, right. So now first let us try to see how the estimator will look like. So now you can see here that what will be the y bar ri hat. Means if you try to remember, earlier we had taken the ratio estimator as say y bar upon x bar into capital X bar. So now I will be having this ith sample mean y bar I, ith sample mean x bar I, and ith strata mean capital X bar I, right. So this is your here y bar hat ri. Now, if you try to remember in case of stratified sampling, what you have done, you had in that case you had all the sample mean something like y1 bar, y2 bar, yk bar, say y bar I. So, you had combined all those by using the weighted arithmetic mean, and the weights were determined by ni upon n, and we had obtained summation I goes from 1 to k ni y bar I upon n, and this was called as a y bar st. So, now the same philosophy is going to be used here, and instead of this here y bar I here, I will try to use y bar ri hat. And this estimator, if you see, this is the same thing, summation I goes from 1 to k ni upon n y bar hat ri, and this I can write down here as I goes from 1 to k wi y bar hat ri, where wi is your capital ni upon n, which is the weight, right. And now, in case if you try to substitute the expression for this for y bar hat ri, this estimator will look like this, which is the separate ratio estimator, right. So, here this y bar I, this is the sample mean of y from the ith strata, x bar I is the sample mean from the ith strata on x, and capital X bar I is the mean of ith strata, right. And you see, we have not made any assumptions that the true ratio remains constant from stratum to stratum, rather it depends on the information on each of this x bar I. Okay. So, now what happens in the case of combined ratio estimator, as we discussed, that we had the sample means, which are actually the paired sample means, say x bar 1, y bar 1 up to here, x bar k, y bar k. So, now we consider the sample mean of x's, which are x1 bar, x2 bar, xk bar, and we try to define here the stratum mean of these, just like we had done in the case of stratified sampling. So, this will become here I goes from 1 to k, say ni upon n x bar I, and similarly we try to define here y1 bar, y2 bar, yk bar, and we try to define then here y bar st as summation I goes from 1 to k, say ni upon n y bar I. Now, I have got here. So, what are we trying to say? That find for the stratum mean of y's and x's is y bar st is equal to summation I goes from 1 to k wi y bar I, and x bar st is I goes from 1 to k wi x bar I. Now, we can consider this y bar st and x bar st as the sample mean, as in the case of ratio estimator in case of simple random sampling, and we can define the ratio estimator as say y bar st divided by x bar st into capital X bar, right, where capital X bar is the population mean of all the x's based on capital N number of units, and here this capital N will be equal to sum of all the stratum sizes n1 plus n2 plus nk, right. So, this estimator is called as combined ratio estimator, and it is indicated by y bar hat RC. So, C means combined, and same thing I have done here also. For example, in the case of separate ratio estimator, you can see I have indicated by y bar hat RS. So, RS means ratio separate, and here RC means ratio combined, right. So, you can see here that it does not depend on the individual stratum units. It does not depend on information on each x bar I, but it depends only on the population mean of all the units, not on the basis of say any particular stratum. So, now we have got here two estimators which are based on the ratio method of estimation as well as stratified sampling. So, essentially we have employed the ratio method of estimation in stratified sampling. Now, we have to find out the properties. So, first we try to concentrate on the properties of separate ratio estimator, and we try to find out its bias. Now, you see you have here two options. One option is that as we have learned or as we have found the estimation error, bias, MSE, etc. in the case of ratio estimation with the simple random sampling. Similarly, you can do here also, and you try to first find all the expression from the basic fundamentals, and then we try to use it. Second option is this: we have already found such expressions, so why to have a proof of them once again? You can also use them directly. So I propose that let us try to use those expressions which we already had found earlier, right? The only difference what you have to now see here, that here the capital Y bar, that is going to define as the weighted arithmetic mean, summation I goes from 1 to k wi y bar I, and this was the same story in the case of stratified sampling also, where we use the simple random sampling, right. So now using this thing, you can write down this separate ratio estimator as say y bar rs is equal to I goes from 1 to k y bar ri, right. So now what we have to do? Now just for your recollection of your memory, when we consider the ratio estimator like this, y bar r hat is equal to small y bar upon capital X bar, this was under actually SRS, and then we had found the bias like this: expected value of y bar r hat is equal to y bar plus y bar upon n into f into cx square minus rho cx cy. Now I have to do the same thing for each and every strata. So this y bar r hat is going to be converted as y bar r I hat, right. So now if you just try to observe what I am doing here, that I want to write down the same expression for the ith strata. So here you can see I am writing here, I can use here a different color pen, say red. So I am writing here I, r is converted by ri. This population mean y bar will be converted as y bar I, because that is from the ith strata mean. So y bar will become say y bar I. Now this f is now going to depend on small ni and capital Ni, so I can write down here as say fi, and this small n, this I can replace by ni. Now what is your here cx square? Cx square here is the coefficient of variation related to the variable capital X, right. So this square of coefficient of variation can be now defined for the ith stratum also. So I can write down here Cix square. So this coefficient of variation also will become Cix, and this coefficient of variation will also become Cciy. Now there is a correlation coefficient. So now earlier correlation coefficient between the variable capital X and capital Y, now it is between the variable in a particular stratum. So I can denote it by here I. So now you can see here, without doing any algebra, I have found the expected value of y bar r I hat, right. So this is exactly what I have written here. Now once I have found this thing, then my life becomes very simple. And here, yeah, means you can see I have given all these expressions, that how these expressions will look like, that x bar I, y bar I, and different types of sx square, sy square for the ith strata, right. So these are the different symbols which I have just used here. Okay. Now I want to study its properties. So I try to find out the expected value of y bar hat rs, that is the separate ratio estimator. So that will become simply summation I goes from 1 to k wi expected value of y bar hat ri. Now you can see this expression we already have found. Where? You see here. So, I can replace this expression over here like this. And in case if you try to take this summation inside, then Wi summation Wi y bar I, this will become capital Y bar, and all other terms will remain as such. So, now the bias of this separate ratio estimator can be defined as expected value of y bar R s minus capital Y bar. So, this Y bar can be brought on the left hand side, and whatever is the term on the right hand side, this will become your bias of separate ratio estimator. But now the question is it the exact bias or an approximate bias? This is an approximate bias. Why? Because this expression what you have used here, this bias of the ratio estimator that was obtained up to the second order of approximation. So, now if you try to see what is this expression is the bias of the separate ratio estimator up to the second order of approximation, right. So, this is an approximate bias. Okay. Now, we try to find the MSE of the separate ratio estimator. So, this MSE we are again going to find following the same methodology what we followed in the case of bias, that we already have found the mean squared error of the ratio estimator under the simple random sampling up to the second order of approximation, and this expression was here like this, what you can see, right. So, this is the expression for the ratio estimator under the simple random sampling. Now, what I have to do? I have to find out the same expression for the ith strata. So, what I can do here, that I will try to convert this expression to find the MSE of ratio estimator in the ith strata. So, for that this estimator here is y bar hat r. So, I can make it here y bar hat r I. Now, this is here y bar. So, I can make it here y bar I. So, this will become y bar I square. This small f is going to be converted into f I. So, this will become capital N I minus small n I upon n I, and this small n is going to be converted as say small n I. This C x square, which was the square of the coefficient of variation related to x, now this will be defined for the ith strata. So, I can put it here C I x square. Similarly, this square of coefficient of variation related to y, this can be made as a C square I y. This correlation coefficient between x and y, now this will become the correlation coefficient between x and y in the ith strata. So, this will become here rho I, and similarly this here C x will be converted into C I x and C y will be converted into C I y, right. And in the alternative form that we had obtained for the MSE of ratio estimator under SRS, this will be converted, f will be converted to f I small n, and capital N will be converted to small n I capital N I, right. And then this here I, this is going to be converted here say I j, and this x I will be converted into I j, right. And this here r, which was capital Y bar upon capital X bar, this will be r I is equal to y bar I upon x bar I. So, you can see here once we have derived this second order approximate expression for the mean square error of ratio estimator, we can now use it here directly, and we can find this expression, and these are the same expression what we have found here. So, now we have obtained these expressions, and now I can find out the MSE of separate ratio estimator like as this. This will become simply summation I goes from 1 to k w I square MSE of y bar hat r I. So, now I can substitute here this the expression for MSE of y bar hat r I, either using this expression or the alternate expression. So, I simply have to substitute here, that is all. So, these two expressions are going to provide you the mean squared error of the separate ratio estimator. Okay, so, you can see it is not difficult, the only thing is this, you have to understand it, right. And now, in case if you want to find out the estimator of this MSE, so that you can estimate this MSE on the basis of given data. So, you have to simply follow a very simple rule, that you are trying to draw the sample on x and y from any strata by simple random sampling. So, in simple random sampling, you know that expected value of S square is equal to capital S square. So, expected value of Sx square, that means the S square corresponding to the variable x, this will be your here capital Sx square, and expected value of S square for the y, this will become here capital Sy square. This is what you have to do here. Yes, the only thing will be, you have here a term r, which was y bar upon x bar, which is now converted into, say, Ri is equal to y bar I upon x bar I, corresponding to which I need here, see here Ri hat. So, this I am denoting as, say here small Ri, and this will be simply your here small y bar I hat minus small x bar I, right. So, now once you try to do it here, and now you have to do it for each and every stratum. So, what I can do for the ith stratum, I can make this expected value of Sx square as, say, expected value of Six square is equal to capital S square Ix. Similarly for the y, and similarly for here Sxy also, because expected value of Sxy is equal to capital Sxy, and now I am doing it for ith one. So, these are the concepts which I am going to do here, and after this you simply have to consider these two forms of the MSE, and you simply have to replace these things. For example, first of all, this c square will be written here as S square upon x bar square, like this, and then you can just replace this S square by S square Ix, nothing more than that. So, if you try to do it here, you will get these two expressions directly without any problem, but I would expect you that you please do this algebra yourself. Means I will explain you once again. For example, in the case of, say here c square Iy, try to write down here as S square Iy upon y bar I square, and then means try to replace this S square Iy by small s square Iy, right. That is all. I hope you can do this algebra very easily yourself. So, now I come to the properties of combined ratio estimator. So, combined ratio estimator, if you remember, it was given by the stratum mean of y divided by stratum mean of x into capital X bar. So, this is given here like this. So, this quantity now I am going to denote by RC hat, right. Now, you can see that if you really want to find out directly this expectation, then it is very difficult to find the exact expression for the bias and mean squared error of this estimator. So, again, as we discussed in the case of ratio method of estimation, we will try to find out the approximate expression. Now, you have to use exactly the same methodology what we have used in the case of ratio method of estimation. Now, there are two quantities. These quantities are here x bar st, y bar st. So, you have to define here two epsilons, one say epsilon 0 and say epsilon 1. Now, they are going to be the function of x bar st and y bar st. So, you see here earlier we had defined epsilon 1 to be y bar minus capital Y bar divided by capital Y bar. Now, I am dividing it defining it here as say y bar st minus capital Y bar upon capital Y bar, right. And similarly, you can define here say epsilon 2 for this x bar st minus capital X bar divided by capital X bar. And exactly on the same way in which we had found the expected value of these epsilons, we can find here that expected value of epsilon 1 is going to be 0. Why? Because expected value of y bar st is going to be y bar, because we have done in the stratified sampling that the stator mean is going to be an unbiased estimator of the population mean, and we are trying to draw the sample here by simple random sampling without replacement. So similarly, this expected value of epsilon 2 will become 0. We had found the expected value of this epsilon squares earlier. The same thing I have to do here. The only thing will be here that these things are going to be replaced by the, say, small n by small ni, capital N by capital Ni, and this s square by s square I, and so on. So this is the same thing what you have done earlier, right? So, and similarly you can find out expected value of epsilon 2 square and the product and expected value of product of epsilon 1 and epsilon 2, right? So I have done nothing here. These are very simple thing. I expect that you can derive it, provided you had understood the algebra in stratified sampling and ratio method of estimation. So now I use the same thing, that we try to assume that absolute value of epsilon 2 is smaller than 1, so that I can expand and I can use the Taylor series expansion and can find out an approximate estimation error of this combined ratio estimator. So this combined ratio estimator can be written as, see here, 1 plus epsilon 1 capital Y bar divided by 1 plus epsilon 2 capital X bar into X bar. This X bar get cancel out, and I have this expression Y bar 1 plus epsilon 1, and then we have here an expression like 1 plus epsilon 1 and 1 plus epsilon 2 raised power of minus 1 times y bar. So this expression can be expanded like this, 1 minus epsilon 2 plus epsilon 2 square and so on, and once you try to multiply 1 plus epsilon 1 in this bracket, you can get here this expression. So you can see here I am trying to now write down here only the expression up to the order 2, because now I know, I have some experience from the past that we will have to retain the terms only up to the order 2. Right. So now in case if you try to retain the terms up to order 2, so I have to truncate it here, and then this expression is given by here like this, and now this y bar can be brought on the left hand side. So then I have the estimation error here given by this expression, right. So now in case if you try to take the expectation of this estimation error, then you will get the bias, and if you try to square it and then try to take the expectation, you will get MSE, right. So now we try to do it here. So the approximate bias of combined ratio estimator up to the second order of approximation can be obtained here by bias of here y bar RC, which is expected value of y bar hat RC minus y bar, and you simply try to substitute here the estimation error which you have obtained, right. And then you already have found these expression, expected value of epsilon which is 0, expected value of epsilon 2 which is 0, and expected value of epsilon 1, epsilon 2, and expected value of epsilon 2 square. So if you try to substitute these values over here, you will get this expression. And yeah, means after this you simply have to just simplify it, and so I try to write down here this Sxy which was earlier rho times Sx Sy. Now I am becoming it, make it here rho I Six Siy, and I am writing it here, and then I try to just simplify it. So now these terms can be written in the terms of coefficient of variation. So and the coefficient of variation of here y. So you can see here this is the expression what we have obtained for the bias of this combined ratio estimator. So you can see here the algebra is pretty straightforward. The main important point is this: you have to understand the basic concept. If you don't understand the stratified sampling or the ratio method of estimation, it will become difficult for you. Okay, right. So here, yeah, as I said, these are the symbols what I have used here. R is the capital Y bar upon X bar, rho I is the correlation coefficient between the observations on X and Y in the ith stratum, and Cix and Ciy, they are the coefficient of variation of X and Y in the ith stratum. Okay. Okay, so now we try to find out the mean squared error. So in order to find out the mean squared error, I simply have to square the estimation error, which I am doing here, you can see, and then I have to retain the terms up to only the second order. So I will say here retain the terms up to second order of approximation. Right. So this is the approximate expression up to the second order of approximation. Now you can see here, you know the value of expected value of epsilon 1 square, you know the value of expected value of epsilon 2 square, and you also know the value of expected value of epsilon 2, where you see you had obtained these expressions here. So these expressions are already here, you simply have to just bring them here and use them. So I have substituted these values over here, you can see, right. And then, yeah, means as usual, I am writing Sxy as rho into Sxsy, and this is for the ith stratum. So now after this, you can see here that means I can simplify it here like this. So and Si square x upon x bar square plus Si y square upon y bar square minus twice of rho I Si x upon x bar Si y upon y bar. So now I try to take this y bar square outside the bracket here, right. So this will become now here inside the bracket y bar square upon x bar square, and this quantity will become y bar upon x bar. So now this y bar square upon x bar square is simply your here r square, right. So just by replacing these quantities, you can see here that it is not difficult to find out the mean squared error of this combined ratio estimator. You only have to understand the steps and algebra and style in the case of ratio method of estimation and stratified sampling. Okay, so now I try to find out an estimator of the mean squared error of this combined ratio estimator. So I have to follow the same thing here, because we are trying to draw the samples by simple random sampling. So in simple random sampling under SRS WOR, you had seen that expected value of S square is equal to capital S square. So now this S square will be replaced by Si square, and now this will become expected value of small Si square is equal to capital Si square, right. And then this will be defined for the variable x as well as variable y, right. So I can write down here expected value of Si square will become Six square, and expected value of similarly here this thing will become Siy square. And yeah, you also have a quantity here r is equal to y bar upon x bar. So this can be replaced by small r is equal to y bar upon small x bar. That means their sample counterpart. So if you just use this thing, and if you try to replace this thing in the MSE which you have obtained here, right, which you have obtained here, you can very easily obtain this estimator of MSE of combined ratio estimator, right. So now you can see you have obtained the MSE as well as its estimator, right. Now I try to compare this combined and separate ratio estimator, and that will give you some interesting illustration, and it is very simple. Right. The main thing is this, that you have to look into the structure. You have to write down the expression of the MSE of the separate ratio estimator, and you have to write down the MSE estimator for the combined ratio estimator side by side, and then you will observe the difference. So you can see, if you try to do it here, I can show you here that this is the MSE of combined ratio estimator, and this is here the MSE of separate ratio estimator. So if you try to put both the things together, you can observe that the difference in the MSE term is coming due to this here Ri, which was the ratio of the sample means of y and x in the MSE of separate ratio estimator, and R, which was actually here y bar upon x bar in MSE, right, in the combined ratio estimator. Now, in case if you try to find out the difference between the MSE of combined and separate ratio estimators, this difference will come out to be here like this. Yeah, you have to do a small algebra, and which can be expressed here in this expression. Right. So, you can see here this expression is essentially depending on two factors. One is here R minus Ri, and second here is this factor. Right. So, this difference delta depends on the magnitude of the difference between the, say, this Ri, which is which are the separate ratios, and the capital R, which is the whole population ratio. And usually about this, the value in this second bracket here, this value is actually usually small, and this vanishes when the regression line of y on x is linear and passing through the origin within each stratum. So, if you remember, we had done the optimal properties of this ratio estimator, where we had compared it with the regression line. So, we had said that okay, if you want to have this the ratio estimator is optimum when the regression line is passing through the origin. So, now the same statement is being continued here, and we are saying that the regression line is passing through the origin for each and every stratum. Right. So, similarly, you can make here some more comparisons, and you can see here that how this value will actually vanish. So, suppose if I try to put this value equal to 0, then the value of this Ri comes out to be here like this, rho I Six Siy into divided by h square Ix. So, this is something like rho I Sixy upon Six square. Right. So, this is something like the value of the regression coefficient for the ith. That is why I said that the regression line is passing through the origin for each and every stratum, because this depends on I. Right. And actually, this is the estimator of the slope parameter in the regression line. So, in such a case, what will happen? That the mean squared error of the combined ratio estimator will be greater than the mean squared error of the separate ratio estimator. But the bias of the combined ratio estimator is going to be smaller than the bias of the separate ratio estimator. So, now you have to see what you really want to obtain. So, now we can conclude that unless Ri varies considerably, the use of combined ratio estimator would provide an estimate of the population mean y bar with negligible bias, and the precision as good as the separate ratio estimator. So, in case if you Ri is equal to R, then the separate ratio estimator can be more precise, but its bias may be large. And if Ri's and R, they are approximately the same, then the combined ratio estimator can be precise. So, that means this y bar hat RC can be as precise as the separate ratio estimator, but the bias of this combined ratio estimator will be small. And it also does not require any knowledge of the stratum means, something like x bar 1, x bar 2, x bar k, because it depends only on capital X bar. Right. Okay. So, now we stop in this lecture, and in this lecture I have tried my best to explain you how one can implement the ratio method of estimation in stratified sampling. The main objective was to explain you how are you going to construct the estimators, which again involves combining the different types of estimators together. So, we have proposed here two methodologies based on the separate estimation and combined estimation, and we also have derived the properties, and while I have shown you that how I can make use of the expression that we had derived earlier, and we can work intelligently. So I would say you please try to practice all the things, revise all the things, and I will see you in the next lecture.